Hello community, so great that you are back. Yesterday Nvidia presented a new AI system, N1. So let's have a look under the hood. What technology is Nvidia using? At first, I always look, about the training time. And if I see 50,000 GPU hours, I think, wow, that's impressive, no? Well, of course, Nvidia uses 1024 GPUs. And then I think, what about the model size? What could the size of N1 be? Imagine, 50,000 GPU. What you guess? A 2 billion free trainable parameter model? Now, you know at this point, there's something special about this model. So, about the training data, yes, of course, we have the web data, we have all the human videos, that is available on the internet. I know what you guess. Then we have all the synthetic data, all the numerical calculation, everything that we have here from synthetic data generation. And then a little tiny bit we have the real world data where humans guide the robot here in their movements. So we have here the perfect training data. Now let's open up this video and there's something beautiful to discover. I mean, if we say, hey, we are calculating this on 1000 H100 GPUs, you might say, what the hell are we calculating for a 2 billion model? No, this is the wrong question. In what complexities are we calculating? So, ladies and gentlemen, may I introduce you to vector spaces? What? Vector spaces from RAG? You say, what? This is impossible. Why again vector spaces? Well, you're not gonna believe it. So, let's have a look at the mathematical spaces that we are operating in. And yeah, it's a complete new way to see this model, but hey, why not have fun? So at first we have a visual embedding space, no? This is here generated by Cyclip 2, our visual encoder, and here at the end I have here from Hugging Face that you have here exactly where you find it, what it is. You have here the archive preprints that explain everything. So here at the bottom you always have here the Hugging Face reference of the model that you can find it. Visual embedding space, beautiful. We have a visual encoder. So each input image that comes in, we have to resize it to 224 times 224 pixels. This is the default. Then embed it and reshape via a pixel shuffle into a set of visual tokens. You remember about the dimension of this mathematical space. Visual embedding space is high dimensional. 100 to thousands of dimensions per token, maybe 10 of thousands dimensions per token if you have a complex scene. Second, of course, our language, the linguistic embedding space. No? Here we have small LM2 language model encoding. And so here Hugging Face, the 1.7b instruct model. So each textual input is tokenized and encoded into linguistic vectors. You know this. The dimension? It's about the same as the visual embedding space, often in the hundreds to thousands of dimensions, normally less than 40,000, about 25,000 might be a good indicator. Then, of course, we have the unified mathematical space. No? We bring now together the vision and the language in an own embedding space, produced after the fusion of the visual tokens and the linguistic token. And here we have an Eagle 2 VLM backbone. The joint embedding after concatenation and encoding, typically 100 to 1000 of dimension here, shared between vision and language. And here you have NVIDIA Eagle. This is available for free on Hugging Face. And if you want to see the paper, this is a real nice paper. This is from the end of January 2025. And here NVIDIA proudly presents its Eagle 2 system. If you want to have a deep dive, this is the paper for you. Then we come to a real interesting state. This is the embodiment-specific state embedding space. Because, hey, we are talking about a little robot, not a little minion walking around in real world time. So we have to know exactly in what state is our robot. Is it jumping, running, where are the arms, where are the legs, in what direction is it looking, what is the current reasoning process. We have to know what's going on with our little robotic system. So we have here the robot state encoded in a unified embedding via an embodiment-specific multi-layer perceptron. What? Not even a transformer. No, we go classic. I mean, Nvidia goes here with this simplest possible neural network multi-layer perceptron. Dimension, usually in the lower hundreds, depend on the robot embodied complexity. How many actuators you have per arm, per leg, per whatever you have in this robot. This is here in the lower hundreds. I think it's a good idea, but just an MLP, beautiful. Now we come to the real action that is happening, and of course we have to embed it in a new mathematical space, and we have an action embedding space. And yes, I know you say, hey, finally, no, actions are embedded using an action encoder. Also, a multi-layer perceptron. It couldn't be easier, I tell you. Similar to the state embeddings, typically ranging from 10 to hundreds of dimensions. I told you there is something beautiful in this. I told you there's one unique feature, and here we are. LAPA. A latent action representation space just for you and me. Now, it is because in the training data I showed you, we have a lot of videos. Now, there in those videos, let's say you have, I don't know, I look at YouTube maybe, there are no ground truth actions where we have really the commands for the actuators here on an arm of a robot. We just have a video. And now comes the beauty. They found a way here to deduct, just watching a video, what the robotic controls should be like if the robot would really move here, or the human being a robot would move here from a frame of the video to the next frame of the video. So just watching here a movie and a person, I don't know, raising the arm or turning the head around is now calculated. How would this translate in real actual commands for, I don't know how many actuators you have in your head, in your robotic head, but you get the idea. And we use an old friend for this, a vector quantized variational autoencoder. And you might say, what? This old stuff? Well, there's an explanation for this. So dimension, usually a compact latent space, 10 to hundreds of dimension, shared across the different embodiments. If you get a term like this, vector quantized variational autoencoder, you just go to my homepage. You don't need to be logged in or anything. You go right next to the post. If you just move there, you see then this little search icon you just put in. My goodness, I have over 900 videos. And there is a probability, you see, this is the result if you do the search. And here, understand vector quantized variational autoencoder for the image generation. This is 2 years ago. I showed you here, even before diffusion, we used here this with the mathematical Kullback-Leibler divergence. Why do we need these terms here? And here we have the Python code in a Colab notebook if you want to see the code for a variational autoencoder with a Kullback-Leibler divergence here in a Keras frame. So everything should be available for you. 900 videos. This is crazy. Coming back now to this video, you understand we have 6 different distinct mathematical spaces embedding vector spaces. So we are absolutely 100% here in vector algebra. Isn't this beautiful? Couldn't be simpler. So we have a visual embedding space, a linguistic embedding space, a unified vision language embedding space, the state embedding space of the robot, the action embedding space, and for the deduction from the huge data set of all the YouTube videos, if we want to understand how should we move our robot just watching here something, our LAPA representation. And I will talk more about LAPA because I think LAPA is the real interesting thing here. No? Source, dimensionality, I think we have now a good understanding. We have now this new N1 AI model by Nvidia. Those are the spaces. But let's talk about now what's really interesting. This is the mathematical function we apply. No? I mean the operators in those spaces and between those spaces. Yeah, it's a little bit different today, but I'm in a good mood and I hope you enjoy this video too. So let's come here to the spark of genius. And yes, this is here from the original paper from Nvidia. It is easy. Have a look at this. You have an image from your sensors as a robot. Now you see this. Then you get a language instruction for me and I tell you, hey, pick up the industry object and place it in the yellow bin. So what we do? we have now in this, if you want, is the special case here, two systems. But at first we have an image, so we encode here the image tokens. And then we have a language instruction, so we tokenize here. We have text tokens. So image tokens and text tokens go in a vision language model, and we call this a system 2 model, no? Because this is a slow model. We're about 10 Hertz. But then we need to know, this is our little robot, my goodness, here's a little bit shaky. Joint positions, base positions, the velocity, all the poses the robot is able to do. So the state that the robot is in. We encode this also here in a specific way. And now comes the beautiful system, and now we have a system 1. This is a fast system. This is about 120 Hertz. Because, yeah, you know exactly what it does. This system 1 generates here the motor actions through iterative denoising here of our diffusion transformer, handling here the real-time motor control at higher frequency. So you see, the idea, in my understanding, is having a system 1, a fast one, and a system 2, a slow thinking one, is similar to a human idea. So therefore, I think the idea of a humanoid robotics emerges here by Nvidia. But hey, the marketing department was working overtime. So we have a fast system for the motor action, that is good, and a slow thinking system, no? And now the interaction between those are the interesting part. But we understood those two systems operate in 6 different mathematical spaces where we have vector operation. Now let's have a look at this in detail. So in the visual embedding space, what is our operation? Encoding. So we have our cyclic 2, our convolutional neural network operation. We have the classical one, the convolution, the pooling, and the activation function, and a pixel shuffle. Okay, that's easy, yeah? In the linguistic embedding space, we have an operation that you know, tokenization and language embedding. Embedding lookup followed by a transformer-based self-attention and a feed-forward operation. This is the classical transformer operation that's happening. If we unify this, you remember my video, now we have a cross-modal fusion and a transformer encoding. So mathematically, just a concatenation in our small language model 2. This means we have a concatenation and transformer-based cross-attention. Careful, now not a self-attention, but a cross-attention, because we unite here vision and language together. And a multi-layer transform operation with our attention normalization and MLP projection, the classical one that you know. Then, for the embodiment-specific encoding via the simplest MLP, yeah, fully connected neural network, nonlinear activation function, ReLU, or whatever you like. Action embedding space, almost as simple as the other one, embedding the action and the diffusion time step with a fully connected MLP layers with nonlinear activations. But now we have this beautiful little thing called LAPA, a latent action representation space, where we have now an action extraction of a latent vector via a vector quantized variational autoencoder encoding. And you remember my videos, please have a look if you don't. We have here a frame of a video. At this frame we call x at a specific time t. And the very next frame we call xt plus 1. And then we encode those two frames, these video frames. And we get a latent vector z at a particular time t. And this encoder, if we have this new latent vector, then we have the decoder. Now we train the system. And the decoder takes now as an input here our latent vector plus the video frame here at the time t, and now builds here the video frame at t plus 1. Remember this? If not, have a look at the video. We have a convolutional neural encoding and a decoding with a quantized latent vector retrieval. Careful, this is not your normal quantized vector. This is a very specific vector. So just take a step back. Why are we doing this number 6? Because in dataset derived from the human videos or generated videos, Explicit motor action, like the robot joint angles or the actuator commands for the robotic system, are not available. We just have a YouTube video. So therefore, we need here, since we have no ground truth labels for supervised action prediction, we need to build them. We need to build some supervised robotic learning approaches purely synthetically from watching a movie. This is not as easy as you might guess it, and therefore we use here a diffusion transformer. So what we do here, we create latent representation, what could be later called pseudo-action labels. So LAPA stands for latent action pseudo-annotation that are created synthetically from a diffusion transformer. And as I told you, transform your initial frame into a future frame, and therefore our pseudo-action label translate here visual sequences directly into actionable representation for the robot control policies. If you haven't seen the video, very shortly, we have in the operation now the encoder, since we are working now here in this particular case with vector quantization. Careful, this is not your normal vector quantization. With a decoder, we do have a specific loss function that is particular to the vector quantized variational autoencoder. If you have seen it, great. So remember the codebook. The codebook have here continuous latent embeddings, creating defined latent action, and each discrete vector corresponds here to a distinct latent action type, since we are operating in a vector space. And those discrete vectors form now clusters in our high-dimensional latent space, capturing thereby meaningful, repeatable action primitives, like grasping, pushing, lifting, whatever is now the robotic action that we deduct from a visual. In the video, I showed you that the training loss function for this particular case of a vector quantized variational autoencoder has three main components: the pure reconstruction loss, the codebook loss from the quantization, and the commitment loss with our famous factor beta, our hyperparameter controlling how strongly the embeddings are committed to the quantized vector. So LAPA is now rather interesting. Eh? We have our latent vector encodes visually observed transformation. Let's say we see on a movie like an arm movement or hand grasping, implicit now as discrete embeddings in a vector space. And this can be mapped further by some simple MLP to an actual robot action space if needed for training the downstream policy models for the robotic system. So you see, within each embedding space, and yes, we just looked at a mathematical operation within a single space, we just have the normal operation. Neural network-based encoding, the decoding, the attention, and, since we're working here with diffusion model, the denoising operations. Let's come to the core idea. We have, of course, the real beauty, the mathematical operations between those six spaces, no? How many do we have? Do you know this? So let's start at the beginning. We have a mapping 1. We have a visual and a linguistic map to the unified space, no? Yeah. Concatenation, subsequent transformer-based cross-modal attention, combined visual and linguistic embeddings. Simple. Then, of course, we have our unified space to the action embedding space. We have our diffusion transformer models, use cross-attention mechanism, and with all the terms, you know this. If you're not really sure about diffusion transformer, in this video a year ago, I explained you here the diffusion transformer, especially the forward and the backward diffusion process, and the critical dimensionality of the latent space, and I explain you why we need this and everything. And if you want to go mathematically a step further, I showed you that having a look at theoretical physics and using here spin glasses for diffusion model, a little bit more advanced lesson, there's a symmetry breaking happening here in the diffusion process. And I show you here in order to optimize the diffusion model and the diffusion transform in higher dimension, it might be important to note that symmetry breaking is happening during the backward diffusion process. And I showed you, yes, from theoretical physics, you know, there are some operators that have some special behavior, but more about this in a later video. Mapping 3. the state embedding space is now mapped to the action embedding space, of course, because this is our current space of the robotic system, and we want that the robot does a specific action, let's say, step forward. Mathematically it's simple, so we have a concatenation of state embeddings within an action in the diffusion transformer blocks, facilitating joint state action conditioning via self-attention. And then we have here this beautiful latent action space that we constructed here of just watching YouTube videos into an action embedding space. And we have our LAPA, our pseudo action labeling here of the pseudo annotation that we purely constructed artificially. You know, MLP-based regression from latent action to actual embodied actions. Beautiful. So you see, between our spaces, we just have 4 mappings if you want. With 4 kind of operation, the target space is always defined, and it's rather simple now from a mathematical point of view. And you might be a little bit disappointed and said, hey, I thought NVIDIA would build something new, challenging, interesting, you know, fascinating, at the edge of technology. Interestingly, they went with old stuff. And then I just read, oh, it's open source. And I thought, okay, so NVIDIA is not giving us the latest insight. No, it's just telling us, hey, if you know the toolbox from 2 years ago, if you put those elements here together, you know, beautiful, and then we can calculate this. Okay, NVIDIA. But the sheer amount of training data is amazing what they did. Huh? Just imagine for every scene, for every configuration, for every color palette, for every movement, for every change in environment, have all this visual data. Unbelievable. However, the mathematical operation between those embedding spaces, the explicit mappings involve now what? Old friends, concatenation, transformer cross-attention, fully connected multi-layer perceptron layers couldn't be easier to transform and fuse information across the modalities that we encounter. And you would say, but this is trivial. This is the latest NVIDIA system? Interesting, no? Here we have it from yesterday, March 18, 2025, NVIDIA GR00T N1, an open foundation model for generalist humanoid robotics. Yes, great. But now they have generated an amazing test data set. 780,000 simulation trajectories for the robotics, equivalent to 6,500 hours or 9 continuous months of movement of human demonstration data, and they generated this in just 11 hours. And you might say, wow, I mean, of course it's NVIDIA, so who cares if you have 1,000 or 10,000 or 100,000 GPUs? But the amount of synthetic data now that they are able just to produce within a day is amazing. And we know everything. We know everything. You know everything about vector fields. So the next step I'm going to show to you, it's really easy, no? Relax. We are just talking about flow matching. You remember how diffusion model works. Now, our transformer architecture, we have a forward diffusion process, what we call noising, gradually adding here some noise to the training data over time. And then we have the reverse diffusion process, we call denoising, no? Learning to reverse this noising process, starting from almost pure noise and step by step removing the noise to reconstruct original data. This is our diffusion. Now, flow matching is now interesting. Flow matching focuses directly on learning the direction of this reverse diffusion process, but just instead of learning just to predict the noise to subtract at each step, flow matching now learns a continuous vector field that guides the data back towards its original clean form. And you would say, hey, wait a minute, again a vector field. Now I understand why you started the video with all the different vector fields that we have, because now we learn here a continuous vector field. So yes, exactly, you see the idea behind this N1 AI system is simple, vector fields. But this vector field is special. Well, yes, of course. So if you want to imagine this, think of a vector field as an arrow at every point in space. And in flow matching, this vector field points now from any given noisy data point towards the direction it should move in the best possible case to become less noisy and more like a real data point. So, like in gradient descent, we now know in which direction the system should move. And we have, of course, time-dependent vector fields. It will change over time as we move through the denoising process, and you can imagine how beautiful this is. Now, in our GR00T N1 system by NVIDIA, this diffusion transformer is the neural network that learns here to approximate this time-dependent vector field. Takes a noisy action, the robot state and the vision language context as input, and simply predicts the direction, this means the vector in our mathematical space, in which the action should be adjusted to become less noisy. So simple, but so beautiful. So we take an AI system, a diffusion transformer, to just approximate here the time dependence here of this particular vector field in the denoising. But should we do a little bit of mathematics? Okay, if you want it. But here, just a simplified mathematical formulation of this process, because you know, of course, that in practice we can really work here in a real-time environment where we have a robotic system with some continuous flow in the inference run. So therefore we have to make it easier. We have the flow matching now discretized into smaller steps, and we hope those steps converge real fast. A little bit of mathematics if you enjoy it. If not, flow matching now is the interesting technique of this paper. Used to train here the diffusion transformer N1 to generate now the real robot actions. Works by learning here a time-dependent vector field that guides here the noisy action sequence toward meaningful, task-relevant action sequences. Couldn't be easier. So this vector field is learned through a process now, you know, like any AI system, we have to minimize the loss function. And here the process is to minimize the flow matching loss function. And during the inference run, when we are time critical here with 120 Hz, this learned field is used to iteratively denoise the random noise into the coherent robot actions. So you see, a simple paper with two surprises. The use of vector quantized variational autoencoders and flow matching in a discrete version that is really able to run at interference speed. So yeah, we're talking about the hardware component of NVIDIA. So you can be sure you have to use the most advanced cards AI systems here, and maybe the most expensive by NVIDIA. What a coincidence. Summary. What we have. Specifications of N1. What are the elements that we're working with? And then we look at the flow between them. What we have. A model architecture class, vision, language, action. This is our model. We have a vision encoding, our cyclib encoder, our linguistic reasoning, long chain of thought, hopefully coming next. A small LM2 language model. For the action generation, we have our diffusion transformer. For the artificial annotation of data from only watching videos without having here the actuated data, we have the latent action representation via vector quantized variational autoencoders. We have as the loss function a specific flow matching loss function for the denoising. And during inference run, the number of iterations they found, hey, with 4 iterations in real time, that's enough for us. Okay. And last point is now the operational flow of GR00T N1. Think about it. What we start with. We have a robot. And a robot receives input from its sensors. No? We have images. I give it maybe an instruction in a human language, let's say in English. And the robot itself is in a particular state. And then we have our vision language processing system 2 kicks in. No? Image observation and the language instruction are fed into our Eagle-2 vision language model, encodes a visual and textual inputs and generates a sequence of vision language token representing the interpreted environment that our robot is and the task objective. Then, of course, the robot has to know in which state I am it myself as a robot. So we produce here the state embeddings. This is our 4th vector space. And then we come to the action. So the action generation via the diffusion. And the vision language tokens, state embeddings, and the noised action vectors now are the input to our diffusion transformer. And then we have an iterative denoising process, denoises here the action vector using our flow matching, guiding by the token from system 2 into robotic state. And then we have the action decoding, because the output of our diffusion transformer, representing here the denoised action tokens, these are the commands, hey, do this, my little robot, is passed here through the embodied specific action decoder, our MLP, and the action decoder translates here the token into our final real motor commands suitable for specific robot embodiment. And the action execution, if we have those, the generated motor commands are sent to the robot's actuators, how many actuators you have in your robotic system, causing it to perform the desired action in the real physical world, in the physical environment, and that process repeats via a closed-loop control system. It is so easy, but careful, there are limitations. And you know immediately, if I talk about diffusion-based action generation, computationally expensive, especially at inference time. So yes, you have to pay Nvidia, and yes, you have to go for the latest technology, even the latest, not the latest technology, but the latest cards, by Nvidia. And I don't think that this is really the latest development, because this would mean that Nvidia is just a perfect, if you want, GPU or AI chip producer, and is not really that far advanced in the process of AI models, building AI models. But maybe Nvidia is more here perfect on the hardware optimization. What do you think about it? And yeah, of course, we need a lot of data. We need data for 50,000 GPU hours. So this dependency on purely synthetic data, this is the main chunk of data that we have, may introduce artifacts. Think about different lighting. Think about the rotation of a human body. How many movements do you see? Your right arm, your left arm, your torso, your head. Maybe you move your fingers in this movement of your complete body. How many different distinct movements should you have at least detect, analyze? What is the flow pattern? The computation can be quite expensive, and don't forget, we are working on 224 times 224 pixels for the complete image. So there we need segmentation, compression techniques, and so therefore I do not hope that N1 is really the latest model, but just here the latest open source model by NVIDIA. And there we have it, a very first look at NVIDIA at the latest 2.2 billion pre-trainable parameter model here. Our AI model with 50,000 GPU hours, trained on more than 1,000 GPUs. AI is absolutely fascinating. And you see, if we look under the hood, it is so simple. It uses here elements that we know, just put together in a particular way. And you know what? Just watching this, we get new ideas how we can optimize here the NVIDIA AI system configurations. If you want to know more, hey, why not subscribe? And I see you in my next video.